Alright, this is number 4 in our projectiles launched at an angle practice. It says a golf ball is hit from the ground at an angle of 30 degrees with a horizontal, and it has an initial speed of 128 meters per second. Ignore the air resistance and determine how long it's going to be in the air, how high it will go, and what its range will be. Once again, this is a same level to same level problem. I know that all golf courses are not completely flat. It's just they're kind of getting bored with their examples of soccer balls and things like that. It's also a nice way to launch something right at ground level. So I've minimized this so I have room to work here. If you need to see the problem again, you can always rewind the video and pause it to see what we've got going on there. So the first step, as always, is to draw a picture of what's going on. So here's our same level to same level. Oh, no it's not. Let's take it back. There we go, same level to same level. And now we're going to draw the path of that golf ball. It'll go, well, that's a straight line. Let me try doing something else here. There's our path of our golf ball there coming in. And we'll put a vector on it right here. Now that's not quite 30 degrees, so this thing is not drawn to scale, but it's just so I have room to write in here if I want it. So this is going to be 30 degrees, and our initial velocity is 128 meters per second. So I got VI. Remember, VI is the initial velocity, is the combination of the X and Y velocities. Theta is 30 degrees. Write out everything you know in the X direction and everything you know in the Y direction. So I've got VIX, VIY. You could have final velocity, so final velocity in the X direction, final velocity in the Y direction. You can have acceleration in the X, acceleration in the Y, delta X, delta Y, and delta T. We're going to start this one off a lot like we did number 3. So if you haven't seen number 3 yet, you might want to go back and watch that. I mean, you can pick it up from here if you haven't, but make sure you're getting number 3 in the worksheet as well. I know the acceleration in the X direction is 0, acceleration in the Y direction is -10. I know my Y displacement is 0 from the beginning to the end. The X we don't know, nor do we know time. So, remember, one of the things we want to do when we see this, we've gotten everything we can figure out written down, is that we want to start this triangle right here. I'm going to try to draw a little more accurate. That looks a little bit more like 30 degrees than what this does over here. But I've got an X component to this and a Y component. I'm going to make the X component blue. And then the Y component, I'll make that this nice green right here. So this just becomes a problem like you have in geometry class. We're going to set this up and use trig to figure out the blue side and the green side if you know the hypotenuse is 128 and the angle's 30. We could use special rights here, but I don't want to get into discussion on how we do special rights, and you're not always going to have a special right triangle. So I'm just going to treat this like we don't know anything about special rights, and we're going to find the initial velocity in the X direction right here, and then the initial velocity in the Y direction over here. So for the X, I know the black is the hypotenuse. I want to know blue, which is the adjacent. The only trig function that deals with adjacent and hypotenuse is cosine. So I'm going to have the cosine of the angle times the hypotenuse will give me the adjacent side, VIX. So punch that in. Make sure your calculator is in degree mode or that will mess it up. So 128 times the cosine of 30 gives you 110.85. So I'm just going to write that in. 110.9. Oh, not in the Y section. See? Sometimes I almost mess that up, and I'll talk about that in a second. And then we're going to say the same thing for the X direction. We're going to say 128. Now the I'm going to say the x direction. Listen to me, I'm getting them mixed up again. And the y direction right here. The y is the opposite side. So the only function that deals with opposite and hypotenuse is the sine function. So 128 times the sine of 30 will give me VI y. So I'm going to punch that in. And I get 64 there. If you knew your special rights, you know it's half that hypotenuse there. So this is going to be 64 meters per second. Now let's talk about this. I almost wrote 110 in the wrong spot. And it's not so much about drawing it accurate, but looking at your angle right here. If it's less than 45, then this side should be longer. If it's equal to 45, this should be a right isosceles because you got a 45, 45, 90. If it's bigger than 45, then the y side, or the up and down velocity, should be larger there. Remember, with vectors, the longer the vector, if it's representing a velocity, the longer the vector, the faster the object's going. So this object, this golf ball, is moving faster left and right than what it is up and down. All right. Now, since I know the initial velocity here in the y direction, the final velocity in the y direction is complete opposite to it. And we should have talked about that in class. If I say I've got a hand and I'm just throwing, this is a hand right here, a very rough drawing of a hand, and it's throwing a ball up in the air. If I release that ball at 3 meters per second, it's going to slow all the way down to hit 0. And then it's going to fall and get faster and faster and faster. The only thing that's slowing it down, if we ignore air resistance, is gravity at a rate of 10 meters per second per every second. And then the only thing speeding it up is gravity at a rate of 10 meters per second per second. So it speeds up and slows down at the same rate. So if it is initially released at 3 meters per second upward, it's going to be falling downward with a velocity of -3 when it reaches the same level here as my hand. So the same thing's going on right here. This thing is shooting upwards, and it's going 64 meters per second. It's going downwards right here at -64 meters per second. But keep in mind, it's at an angle. I'm just talking about the component. The component in the y direction, 64, and then -64. The x, however, is going to be, since it has 0 acceleration, is going to be going 110.9 meters per second. So knowing these facts over here, if you go back to the kinematic equations we talked about when we did one-dimensional motion, we said that the final velocity is equal to the initial velocity plus acceleration times delta t, or we call that VVAT. We can use the same equations from that chapter on one-dimensional motion, but now we can actually assign a x or y direction to it. It's important that we do that. So this is going to be in the y direction, y direction, the y direction right there. So when I put in my final velocity of -64, that equals the positive velocity of 64 plus the acceleration of gravity times delta t. So this gives me -128 is equal to -10. This should be meters per second times delta t. Divide both sides by -10 and you get 12.8 seconds equals delta t. That's how long it's in the air. So this goes in as 12.8. And remember, the x and y direction have the same amount of, the time is the connecting factor between the two directions. That's the thing that's always going to be the same between the two. So that answers question A there, or part A. The next one, I'm going to jump down to question C because that's the easy one to answer after figuring out A is how far is it going to go. I know that if I want to know how far I'm going, and I know what my velocity is and what my time is, or my average velocity here, I can figure out how far I'm going. If I'm going 20 miles an hour down the road for 3 hours, I've gone 60 miles. Just multiply the two. So this is going to be my 110.9 times my time. What did I find for my time? 12.8. And that will give me my displacement. And so 1425.1 meters, that gives me delta x. That's our second part right there. Now, how high will it go? There's a couple different ways we can answer this. One of my favorites is to stop this problem halfway through. So let me erase some of this stuff, get it out of our way. Let's see. Let's suppose we stop the problem right here at its maximum height. Okay. Get rid of that too. Well, at its maximum height, what is the velocity in the y direction? If you think about it once again, here, let me draw that horrible drawing of my hand there. I can draw a better picture of the hand, just not on the computer. And so as the ball goes up, going straight up, if we're ignoring the left and right motion, and then back down, remember our velocity, anything you toss in the air, if you're going to pause the video, toss something up in the air. Grab a small pencil or something that's not so sharp, throw it up in the air. Just, you don't have to throw up in the air very high, just straight up, maybe a foot or something in the air. Watch the velocity. As soon as that pin hits its maximum height, the velocity is 0. And then it starts to speed up as it goes downward. The same thing's happening in the up and down direction here. It goes from really fast to slow, 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 slow to 0, and then it falls down and gets faster and faster. Now left or right, it stays at 110.9. So I know that at its maximum height here, the final velocity is 0. So I can put that in right here. We know the initial velocity is 64. And then the acceleration is -10. And then times delta t. Now remember, this delta t is halfway through the height. And really, it should just be half of the 12.8 that we got right here anyway. But just checking it, you can pause the video if you want, do these calculations, and you would get that delta t is 6.4 seconds. So that should make sense. It should be exactly halfway through its height when it reaches its maximum height. And it's going to take another 6.4 seconds to hit the ground, and that gives you 12.8 there for delta t. And sometimes I even solve it that way. If I want to do part A, sometimes I'll take and set it up like this, solve for my delta t, and then double it, and I'll have my flight time. So anyway, that's how we figure out how long it takes to reach its maximum height. But the question is, what is the maximum height? Well, now we need an equation that will give us delta y. So remember, once again, in the one-dimensional kinematics, we would have delta x is equal to your initial velocity times delta t plus 1/2 at squared. Once again, we're going to do the same thing, except we're going to make this go into the y direction. So instead of saying delta x, we're going to say delta y. Instead of just initial velocity, because we're not talking about the velocity at the angle, we want the initial velocity in the y direction times how long it's in the air, plus 1/2 times the acceleration in the y direction, some texts use g here, times delta t squared. And let's substitute what we know here. We don't know delta y, so it's going to stay the same. That's what we're looking for. We know the initial velocity in the y direction. It's 64. We know the time. The time is going to be 6.4. Oops, put an extra parentheses in there. 6.4 seconds. Plus 1/2, and remember we're using 10 for gravity in this case. It's going to be -10. That's meters per second squared. Times delta t of 6.4 seconds. And that 6.4 is going to be squared there. So I'm going to pause the video and do the calculations real fast. I suggest you do the same just to make sure that you get the same as I do. Alright, and doing that, I got 204.8 meters. And that's going to be my max height right here. And that gives me part B right there. Okay? Thanks for watching and hope this helped you.